In today's lecture, we're going to finish our discussion of object-oriented programming languages such as Java, the four characteristics of them. And we've seen examples of all these characteristics even if we haven't called it out explicitly. Encapsulation, we've definitely called out explicitly many times. Inheritance, polymorphism, and abstraction. So of these four, we've talked about encapsulation and inheritance, a little bit about abstraction, but not too much explicitly about polymorphism, but you have seen it in action. So encapsulation. So you have private data, for example, and public methods. But member visibility, both for methods and for data, is in the class designer's choice. So encapsulation, putting in the class designer's control what parts of an object or a class are visible to the outside code. Inheritance. This is from general to specific. In inheritance, a derived class inherits the properties and methods of its base class, then extends those characteristics, becoming a more specific type. So if you envision an object-oriented hierarchy as an inverted tree, with the root at the top, that root being object, then that's the most general type of object we have. As we develop our object-oriented design, we're getting more and more specific behavior as we work down the object hierarchy. All Java classes inherit from object, gaining, among others, the toString method and the equals method. So there's other methods as well, but toString and equals are the ones we've encountered the most and the ones you'll encounter the most in your day-to-day work. In object, these methods are very general, but they're reasonable. For example, the toString method, as we've seen, prints the name of the object's class and then its memory location. Well, if you consider object, and at the level that that's working at, that's what it knows. It doesn't know anything more specific about the object's or the class's behavior. You need to override these to get custom behavior for your more specific class. Polymorphism. Poly means many, morphism means many forms, so many forms. An object handle can be declared as a more general type, but it will behave as the type that is actually instantiated. So instantiated means the actual object creation with a new keyword. So, for example, object O equals new student. Object is very general, the most general type. Student may be very specific. It may have an inheritance above it that has many levels. But this declaration would work because student as a class is an object. So O.toString, even though we've declared it as a very general object, would behave with the student's toString method if one is implemented. Abstraction. The ability to express an idea without knowing the exact implementation. And we do this in discourse all the time. For example, animal. An animal eats, it moves, it breathes oxygen. But there's no critter that's just an animal. So an animal is an abstract notion. When you get down to specific types, then you know more about how that animal eats, how it moves, how it breathes. For example, a vegetarian eats plants. A carnivore eats other animals, eats meat. How it moves. If it's a fish, it swims. If it's a cat, it may run. And that also counts in how it breathes oxygen. So a fish has gills, and a land animal has lungs. So there are all types of animals, but so we have these general notions of them, abstract notions of how they behave, but we have to get to a specific animal before we get to specific behaviors and capabilities. So here's another abstract example. Comparable. The objects of this class using compare-to know how to compare each other. So if you say you implement comparable, you have to implement compare-to. The compiler makes you do that. So the compare-to in the sort routine, say the sort knows how to put objects in sorted order, and it has very sophisticated logic to do that very quickly. However, what it doesn't know is this is a collection of some types of objects. What is the object's view of what is less than, equal to, or greater than? There's no way that the sort can know this for all classes that might be created. the class needs to implement comparable to teach the sort method what order the objects of that class go in. So let's recall our shape example from our previous lectures. We have a circle and we have a rectangle. So a circle is a drawable. And remember that we did rectangle and we implemented drawable and printable for rectangle. So circle is a drawable and rectangle is a drawable as well as being a printable. So in the next lecture, I'm going to get into specific Java code, and we're going to change the object hierarchy a little bit. We're going to introduce an abstract class called shape, and that will inherit from drawable and also inherit from printable. Then the rectangle will inherit from shape, and the circle will also inherit from shape. So rectangle is a shape, but then moving up the object hierarchy, shape is a drawable, and shape is a printable. Therefore, rectangle is also those objects as well, working up the object hierarchy. You can say the same thing about circle. So shape will be an abstract class. An abstract class is in between an interface and a class. So a class, a non-abstract class, is known also as a concrete class. All methods are implemented. A shape, an abstract class, the shape here, will have some characteristics of an interface, that is, some unimplemented methods, while mixing in some implementations as well. So we will see in the next example, I'll point out explicitly all these characteristics: encapsulation, inheritance, polymorphism, and abstraction.